Hello, today we're going to talk about the stack optimization, an optimization pattern for the Java virtual machine that is hopefully already implemented. So, there is James Gosling, the father of Java, and I believe he belongs to the Hall of Fame of developers, joined by icons such as John Carmack, Jeff Minter, Kernighan Ritchie, Richard Stallman, Grady Booch, Anders Helsberg, Jonas Drustrup, and then Linus Torvalds. But in this video, let's focus on James Gosling. One of the things Java has always been criticized for is its memory management architecture with the garbage collector. In an interview, James Gosling said something like the following on why he gave Java the garbage collector.
I gave Java the garbage collector because I was tired of sitting in the middle of the night analyzing core dumps.
And that's of course very true. For any C or C++ programmer, finding bad pointers or memory leaks is a normal part of your working day. But nevertheless, this garbage collector stirs up a lot of feelings from the developer community. One you may frequently hear is,
"It is not logically ethical to not clean up the mess you allocated at a time when it's not needed anymore."
Okay, so let's briefly look at the garbage collector. Well, one of the most common implementations uses the mark, sweep, and compact algorithm to ensure that non-used objects are removed from memory, and that the heap is compacted to eliminate the death spiral side effect of fragmentation. And of course, running this process has an impact on the normal flow of execution of the program. The amount of impact depends on how you run this process, and there are different alternatives, for example, stop the world, incremental, and concurrent. So, we have the following different views on how memory should be recycled in programming. On the one hand side, the Java way, using the garbage collector, potentially the concurrent one, which task is to take care of this in the background. And then the C++ way, where the mentality is that the memory should be freed up explicitly through code at the point where it's no longer needed. So what's the best? On the one hand side, it's convenient and time effective not to have to care about when memory is freed. On the other hand side, you don't want to risk any potential negative side effects from garbage collection that you do not control. Well, even though other alternatives also exist by, for example, using smart pointers, let's look at how the Java virtual machine could be optimized to reduce these potential problems significantly. Hey Larry, hey Barney, wouldn't it be possible to optimize the garbage collector in Java so that it becomes more efficient? I mean, behind the scenes, so that the programmer would not have to care about it.
Aren't you a little old-fashioned now? I mean, what's the point? We live in the distributed computing era of the 21st century. Just throw more hardware at it.
Yeah, why don't we do it as we always do?
You mean completely ignore the power of a single box and unconditionally surrender to stacking independent boxes on top of each other to achieve linear scalability through a share-nothing architecture? Hey guys, you know I'm all for that. But can we at least just not try to think if there's a smarter low-level way before we decide on this architecture and continue to build out our COM stack, walking through the low-level, highly efficient UDP and TCP stacks upwards, adding XML as payload and dynamic service discovery through fully SOA-compliant web services, and then why not throw in an application server that weighs hundreds of gigs to shield you as a programmer from any resemblance of fun? And then let's run that on Hadoop or something like that to get all that stuff distributed across all of those boxes, and then we use some high-level construct to structure and query our distributed unstructured data such as MapReduce, Java, Pig, Python, HBase, or Hive. No, seriously guys, don't get me wrong here. You know I'm all for many of those things. But if we throw all of these things together, it's going to be very hard to focus on the one resource we want to saturate and have work as much as possible, the CPU. And with this stack, we will not make much use of it. I mean, the objective of any performance optimization is to saturate the CPU, then we scale through distribution. So let's work on one box for now. Once we optimize that, then we can scale that linearly through distribution and share nothing. Come on, it will be fun. We then actually have one system and environment we can control, and we would be honoring the fundamental work of the guys in the Hall of Fame. And by optimizing the low-level component, we would be conserving resources and money by not requiring as many boxes in the final solution.
Okay, yeah, I agree. Let's talk about the Java garbage collector then.
Yeah, okay.
What's your angle here?
Yeah. What are you getting at?
So if we compare the differences in memory management between C++ and Java, we would come up with the following matrix. For heap allocation, they are the same. Memory is allocated explicitly through the new operator. For heap deallocation, they are different, as previously described. C++ requires explicit use of the delete operator, whereas Java memory is implicitly freed by the garbage collector. And then finally, C++ contains one more declaration construct, which is not available in Java, declaring objects which are allocated on the stack. Let's explore this one in more detail. What does declaration by value on the stack mean in C++? Let's write some code here. We can now see the code snippet on the left and the stack call frame layout on the right. Let's look at what happens when code execution enters the doIt function. Well, first of all, the CPU assigns a new value to the stack pointer register. This new value is incremented to allow storing all of the parameters of doIt, the return address where code execution should be resumed when execution of doIt is complete, and all the local variables declared within the doIt function. So a pointer to this, the object address, and argv1 will be stored as parameters. And the TC variable, which is an instance of the timer class, will be stored within the space slotted for locals. And once the execution of doIt is finished, the execution will be returned to the caller of doIt, located at the return address. And the stack pointer register will be set to the caller stack call frame address. So the entire stack call frame memory segment of doIt is thereby discarded. And the memory allocated for TC is reclaimed by this simple and extremely fast reassignment of the stack pointer register.
Well, reclaiming the memory for TC is of course super fast.
Yes, that is only a couple of assembly instructions, and they are needed anyhow.
Yes, would be much faster than a conventional heap allocation.
Yeah, and it completely takes away the need for defragmentation or compaction.
Are you guys thinking what I'm thinking?
We think so.
You are thinking if that can be done for Java.
Correct. Of course behind the scenes by the JVM, so no changes in the code. So we can now look at modifying our JVM memory management subsystem in Java to do the following. Object allocation is as usual done explicitly through the new operator, and it is put on the heap, unless a stack allocation is possible. If a stack allocation is possible, then the object is allocated on the stack. The object deallocation is as usually done through the garbage collector if the object is on heap. But in the case where the object is allocated on the stack, we now have an alternative approach to deallocating memory, which is to simply reassign the stack pointer register. So let's say that we have the following function skeleton of foobar, a declaration of a variable named TC. Well, first during JIT compilation, all code, including timer class, needs to be instrumented to see if it can be allocated on the stack instead of the heap. Whenever possible during execution, put instances of timer class on the stack rather than on the heap. And if it cannot be put on the stack, retract from such strategy and put it on the heap as usual.
Wow!
So where can we put objects on the stack? Let's look at an implementation of timer class. So, if a timer class only has 2 long primitives as members, then we know at compile time that an instance of timer class will require 16 bytes of memory. Therefore, an instance of timer class can be put on the stack. Let's look at a more complex example. In this example, the implementation of timer class contains 2 date objects as members. Whether or not timer class instances can be allocated on the stack now depends on 2 things. First, whether the bytecode inspection of date yielded that its instances can be put on the stack. And secondly, whether the date instances are self-contained within the timer class instance. In other words, that they do not need to survive beyond the execution of doIt. Let's look at another code example. And in this example, we can conclude that stack allocation is not possible, even if the previous example using date instances would be. The reason for this is that TC is assigned to a static variable called _global. This variable survives the call stack frame in which doIt operates, so therefore TC must as well. Guys, we're on to something here.
I agree. There are some cases we need to continue to analyze though, but it could save a lot of CPU and memory resources.
Yeah, we need to look at growing array fields and if we can support dynamic object sizes and stuff. But already this could work for a large percentage of objects.
Great! Let's start coding it. Lunch first?
Absolutely.
I'm in.
Sushi?
Great!
Yeah, yummy.
Let's go! Thanks a bunch for watching.